given the task to talk about earthquake risk in the Himalayas. Here the title, in this title, there is the word risk. And of course, already in the introduction, the word hazard has also been mentioned. And for the student, I would like to underline these are two different things. The hazard is the probability of an earthquake and a particular acceleration to occur, whereas the risk concerns the losses. So with this in mind, contents are thoughts about human relationship to earthquakes. That's generally what do people, humans, think about their environment. Then a few notes about great Himalayan earthquakes. If you're not, probably some of you are very familiar with this, others not so much. Estimating earthquake fatalities is what I do. And we do this in real time. You see, by real time, I mean within minutes. This word here, real time, within minutes after an earthquake. And then in scenario mode, scenario would be, okay, in the future there will be earthquakes and we are trying to model one from what we know and then calculate if that earthquake would happen, what is going to happen in the future. Then I come back a little bit to seismic hazard assessment. I think it is wrong, and the engineers who are the engineer experts who are present might not agree with this, and they might have some doubts. Nevertheless, I'd like to discuss it then. Finally, who are the foremost victims of earthquakes? And a few words on how to prepare. So that's my plan. So now, of course, we know the highest mountain chain on Earth is the Himalayas. And in red, I marked that it's probable that the Himalayan region will overtake in China as the country of the greatest number of earthquake victims. Right now, it's China, because China also has very large earthquakes. Just to give you, the people who are not so familiar with the Himalayas, an idea of what earthquakes have happened in the past. You see on this table, on the left is the date, the year is of interest, and then of interest is the magnitude column here with the larger earthquakes in red. And indeed, you can see there's about 24 large earthquakes that we know about in the Himalayas. So this is definitely a very, very earthquake-prone area. And that's an old slide showing some of the supposed rupture areas in red. And the seismic gap, I used this slide, although the newest ones are not in there, because it shows that seismic gap that I will come back to in a later slide. So what is the cause of earthquakes? And when people cannot understand something, they invent explanations. And that is true for a lot of things in the life of humans. So this is the Japanese explanation, the historic myth. There is a catfish that is kept in place by a god with a big rock. And when that catfish wiggles, then we have an earthquake. I like this explanation from New Zealand, from the Maoris, a little better, because here is a picture of the earth, and that is goddess earth, has a womb, and in this womb is a god not born yet. His name is Ruau Moko, and when he turns over in the womb, then it's an earthquake. And just on the side, when he gets bored, that's the end of the world. So in Europe, however, the prevailing view at the time of the 1755 Lisboa earthquake, the view was God punishes sinners. This was a big earthquake, still not quite understood, category 8 probably. Offshore must have been, and it was Good Friday, and people were in churches, and the churches collapsed and killed them, and there was this big uproar that now these are sinners and they must be punished. And there was a monk running around talking about punishment and then more punishment needed. However, there was also a philosopher, this is Voltaire, who made a stand saying it's not God that does these things. That is nature that generates natural phenomena. So the cause of the Lisboa earthquake is not a punishment by God. Another philosopher, Kant, made a small step farther by trying to find reasons for why this earthquake happened. It's the same opinion as Voltaire. God does not make it, it's nature. And what are the reasons? But his, as philosopher, he didn't make much progress, but this man made progress. John Mitchell, he figured out that earthquakes are caused by rock movements, and the seismic waves or the shaking is due to propagation of seismic waves. That is real first step of science. So the Lisboa earthquake of magnitude 8 caliber ushered in natural science in Europe. And that is a really, really important turn of attitude that is worthwhile noting briefly. Can earthquakes be predicted? Of course, more recently, in the last couple of decades, there was a strong activity on this topic. In China, it was a duty, similar to the order in the 1970s in the Soviet Union that seafloor spreading has to be disproved. That was Belousov, who was the Tsar of earth science in the Soviet Union, and he simply ordered that seafloor spreading does not take place. That's it. Of course, you know that that was wrong, and it was really not a feather in the cap of leading scientists that you have somebody ordering everybody else to believe some nonsense. Some of the prediction schemes in the 1980s were not much better than the story of Namazu. Now it seems that earthquakes are too complex to be predicted reliably. I have started working on it because I didn't see anyone making progress. I changed my focus. For the last couple of decades, I have concentrating also on predicting something, namely earthquake damage and number of fatalities and injured. And that's the main thing I want to talk to you about. But first, I want to just, for those people who are not so familiar with the Himalayan earthquakes, and I think there are many students in the audience who this may be new for them, I don't know. This is a figure from Willem, 2016. The top shows a map of the Gorka earthquake. You see the date up there and the magnitude. The rupture area is purple, and Willem was quite interested in the afterslip. Many times after earthquakes, there is afterslip. That's in yellow. You notice the two, here is afterslip in centimeters, and the rupture is in meters. And of course, us, the rupture interests most, and the cross-section perhaps is what students should consider. This type of figure has been shown many times, but for this particular earthquake, Willem showed that according to his information, the maximum slip is about 7 meters, and cross-section is almost north-south. You see where in the map what the cross-section is. That dashed line shows it. And the dimensions of the earthquake, notice that too. Look back at the map up here, the lengths of a rupture. Ruptures started here in the northwest, and then it was about 150 kilometers long or something of that order. So that's the type of earthquake that we have to expect in the Himalayas. And here there is this note that the 1505 earthquake might have been a magnitude larger than 8.6 probably, and it's located where it's brown, from the brown area to the west. Okay, this is sort of the typical earthquake. Now, cartoon of an earthquake with damage is shown here. We have the earthquake hypocenter at depth, and then the rupture is assumed to come to the surface and rupture the surface. And then there's various damage shown of buildings. So it's possible that a structure near the earthquake is so solid and on solid ground, it is not damaged. And structures rather far away, if they are on a lake bed or similar unconsolidated surface, they completely collapse, although they're quite far away. And all of this is done by the seismic waves that are. So this is what I am trying to estimate. How great is the damage and what are the consequences? This is a photo of the Kashmir earthquake where of the order of 80,000 people perished. And it's really very serious. This is a photograph of the rescuers in the Gurkha earthquake. They are located in Kathmandu, and I've written an article about this with the title that you see here, Report Estimating Quakes Death Toll to Save Lives. That is the title that journal Nature, who published my article, imposed. I had a different title, namely this one, Media Reporting Contributes to Injured Dying After Earthquake Disasters. It's a very sad story, but it is a fact. It is terrible, in my opinion. Here I show how slow media and governments are in reporting earthquake fatalities, meaning in understanding how extensive was the damage, how serious is the disasters. These are 4 different earthquakes. Each frame is an earthquake, but let's concentrate on one, the first one here. So this is the Wenchuan earthquake. It's magnitude 7.9. As a function of time, which is in hours in this slide, unfortunately. So, okay, we can divide by 24 to give dates. So after 100 hours, that's about 4 days, right? And shown is in the vertical direction, fatalities in thousands. How many fatalities were reported? Each dot is a report of, here it's only the Chinese news agencies, in the other slides is BBC and other news agencies. So after about 4 days, here I show is the 100 mark, the Chinese government thought the earthquake had only killed 20,000 people. And that was, on this basis, they formed their rescue operation. Now, China is a very big country that has many soldiers that could, infinite number of soldiers that could be activated and sent to rescue people, but they were not sent there, although the ultimate count, see, up here, the ultimate count is nearly 90,000 people dead. And they thought for quite a few days that it was only a fraction of that. I am kind of upset about this because these agencies should, also the government of China and the agencies, BBC and so on, who report this, should not report this garbage at the beginning, at the very beginning. It's standard. 2 people dead, then it's 200, then it's 2,000, then it's 20,000. Okay, this is quite upsetting when in fact there are 2 estimates available, my estimate and that of the USGS, and we are very similar in our estimate. And if you have 2 pieces of information, then news agencies always say, if we need 2 pieces of information too, otherwise we don't believe anything. So they have 2 pieces of data. So I want to show you now how I estimate fatalities and injured in the case of any earthquake worldwide. The earthquake can happen anywhere. So at the top of the left, I show just a model of an earthquake happened someplace, and at the bottom is the aim, help the injured. So then the earthquake sends out waves, and the waves arrive at seismographs. So the source parameters are estimated. And Geoforschungszentrum Potsdam is really, on average, the first agencies that reports this. That is latitude, longitude, depth, and magnitude. All of these parameters are a little bit suspect at the beginning, they carry errors, and especially the depth is quite a bit uncertain. And I come back to the errors that exist and that are later improved and see how much trouble they cause. Then, as a next step, is this input of coordinates and magnitude. I will use the Earth transmission properties to estimate the ground motion in my computer program. And I would have a number of different attenuation equations that I could use. Oops, I'm going which way? Wrong way. Aha. Building fragility database I need. I need to know for the whole world what are the buildings or how are they constructed, how fragile are they with respect to shaking, because these Earth motions that I calculate will impact the buildings, and then the buildings will receive some damage. Some of the buildings may collapse, and then the collapsed population or the collapsed buildings fall on the population. And so I need a database for the population to estimate how many people are now dead and how many are injured. And that is then the estimated result that I produce. Building damage, estimated number of fatalities, estimated number of injured. That is my product, and that I put on the website. And if you want this, you can subscribe, and this is free. You receive that estimate, and I show you later what form that estimate takes. So that's my job of QLearn. Then after that, governments and rescue agencies have to swing into action. Based on the US Geological Survey and my estimates, such government agencies can then decide, yes, we want to mobilize and offer help, or not mobilize because local people can take care of the relatively small damage and a small disaster. And of course, the disaster manager have to mitigate or accept help. They have to make a decision, how do we help the people, the injured people that can still be helped? So that's the process. Now, QLearn real-time output. Real-time, it's near real-time. I'll show you what. The fact is, first an earthquake happens. And here, this is in the earthquake epicentral area. And nobody knows about it anywhere in the world except those people who live right there. And communication centers, communication towers are usually damaged, and there's no information flowing from the area itself. And then my report looks like this. At the top on the left side, where it was this earthquake, Iran, latitude, longitude, magnitude, depth, and what's the source of this information? Geoforschungszentrum in Potsdam. Then here are my estimated losses. I think in this case, the injured numbered somewhere in this range, and the fatalities were between 100 and 500. The map is showing all, each dot is a settlement that is in my database. When the dot is red, then the mean damage, the color of the dot is mean damage. Red is pretty bad. Damage grade 3 and larger. Then blue is on the outside, as you can see, and that damage grade is smaller than 1. So down below, I have some remarks that I make up. And down here in the right side, I have estimated exposure, number of people for different intensity levels, intensity 5, bis 9 in this case, and my estimated numbers of intensity. And that is the kind of alert that if you want to, you could subscribe at the website of ICES, icesfoundation.org. Okay, conclusions of this kind of work after about 1,000 near, or by now it's maybe 1,300 near real-time alerts, that is after 80 years. My conclusion is, my estimates of number of fatalities are usually on median 30 minutes after the occurrence of an earthquake. So it takes me about 30 minutes to, that is, first I have to wait till GFZ has information, and next I have to get out of bed and calculate. Then my estimate of number of fatalities are correct, usually within factors of 2 to 3. But sometimes they are wrong, but that's kind of rare, but there are reasons for that. My estimates of fatalities are similar to those of the USGS. So based on two information sources, the news media should distribute the information that there are thousands of fatalities expected, not just 20. Now, what is lacking is a world data set on hospitals and schools. And that is a problem in my view, because obviously hospitals and schools are critical facilities, especially schools. In the Gurkha earthquake, the school was not in, it was Saturday. And for that reason, Billam estimates that 10,000 lives of children were saved because they were not in the schools that collapsed. That is special for Saturday, and I don't have in my computer yet a program to distinguish Saturdays from week works. Well, it's a matter of money. If I had money, I would do it. Okay, let's switch gears and say, okay, we talked about near real time, and now we're going to scenario losses. What is the scenario? Say, okay, we have places in the world where there's likely earthquake going to happen because there has been a previous one and it's been a long time and it's an increased probability at the present. And so let's see what happens if that fault that we know it exists will rupture. The purpose, of course, is quantitative information for population and authorities. Prepare is the message that we like to give them. I don't think they'll listen. Okay, as the first thing in such work, we say verification of calculation. So I take intensity maps of all the earthquakes. This is a better one than the first one. That's India. They're all Indian Himalayas, I should say, earthquakes. And again, the color of the dots are the intensity of shaking in this case, not mean damage, intensity of shaking. And I am trying to match with my calculated intensity of shaking the contours that someone else has drawn on field reports on intensities. And so then I come up with my model of an earthquake, which is I put a line like this in it and say, this is the rupture line, and then calculate the nearest distance from this line to each of the settlements that are in my database, and I'm trying to match the original observation. And then I do this for several earthquakes, maybe the Kashmir earthquake here on the lower right, because it was a huge earthquake, is the most illustrative of that. There are many, many settlements, and you see that in some parts I matched very well, but in other parts not so well, because of course the soil conditions are different in different directions and locations. But that is the work of verification. Can I use this program to reasonably predict the shaking and then from that calculate fatalities? And I think the answer here is yes, I can. Oops, I don't even see this one. That is now a scenario for a model of human losses of an example of a repeat earthquake. I gave it the magnitude 8.7, and it's the earthquake that supposedly happened in 1505 in the Himalayas. A close-up, this figure on the lower right shows the position in the subcontinent of India. And this is a map of the settlements. And of course, you can see that I took a line source that went from here to there to model the earthquake. And then I could also make the same map for mean damage. First the intensity, then the mean damage. And from that all together comes this conclusion. If I assume this kind of large magnitude, I estimate that the fatalities may be in the order of 500, 500,000, and 1.7 million injured, and 75 million strongly affected people. Strongly affected, I count all the people that are in my database in the area with intensities larger than 6. 6 is an intensity that already will do some damage to poor buildings, but not that serious. So strongly affected, I call those people intensity 7 and larger. That would be 75 million. These are very sobering numbers, I'm afraid. Now I want to mention just one error source. There are a number of error sources, and if I wanted to give a lecture only on Q-Lerma, we could explore the error sources and what's the matter with some of the input. But I just showed this one. Initial point source versus the real extended rupture. So when I get an SMS, I get coordinates for latitude, longitude, and depth and magnitude. That's it. That's a point source. But bigger, that's okay for a magnitude 6, 6.5 even is still okay. But for magnitude 8 plus, it's a long, long rupture, and a point source is a poor representation of the source. This is a comparison of, in the case of the Wenchuan earthquake. On the left, I have a point source, and I have no choice. I don't know this fault. I never heard of the Wenchuan fault before. I would know this San Andreas fault, but not this one. So I just have no choice. I have to use circles, a point source, and that's what I get as a map of damage at first. But later, when I know everything, I get this figure on the right-hand side with an extended source of 300 kilometers. This is a rupture of 300 kilometers, and that is clearly very different. And whereas on the left side, I would say all these people up in the right corner, northeast corner, they're okay. Nothing happened. Not true. The earthquake rupture came to them and was absolutely terrible for them. So that is one of the errors that happen. And this can also happen when there's an ocean. The earthquake rupture might start in the ocean and then propagate towards land where there's a city. And I did not know that the rupture ended practically under the city. Okay, so that's one data necessary. Okay, I said it, we need the people with coordinates and then the building stock. So here about some words about the building stock. Shown as a function of the shaking intensity here at the bottom. And this is the percent of destruction. What's on the slide? Vulnerability classes of buildings. So there is a building that the engineers have called a structure. This is an engineered structure, and it will, no, wait a minute, wrong. The E here, of course, sorry, this E here, that's the strongest structure. It resists shaking, and you need to shake it a lot until you get some damage out of it. Whereas the A is the weakest, the worst kind of building, and here it ends up at 100% destruction. That is percent destruction. So we need to know how many buildings of each kind are in a particular settlement. So we make up pallets of a settlement. We say, okay, we have a settlement, and in it, we think, from all we know, the percentage of buildings in these different classes are as shown, that's in percent. So, for instance, this would be a village in the Himalayas. Most buildings, 60% almost, are of the weakest structure, and there are no E or F building. F is even stronger than E. There are none of these, and very few medium strong buildings, but these are very weak buildings. So we need to know that. Next, we have people that are distributed in these buildings. And depending on the size of the buildings, the two figures, people in the different vulnerability classes is different than the number of buildings, because the worst buildings are kind of small buildings. So they don't contain a lot of people. So most people actually live in B class buildings, according to what we know. And then from this results a, what should I say, an unfairness towards poor people. See, this is a case from Mexico, where as a function of intensity, which is shown at the bottom, here that's intensity, the mortality per mil is shown. Mortality being how many, the fraction of people dead. The red curve, where there are lots of people dying, that's villages. And then the orange is an intermediate type of town. And then the big cities have better constructed buildings. And this is the black dots at the bottom. And many fewer people die percent or per mil wise in the city. And that means that, and of course in the city, it's also the same spectrum. The rich people, they're okay, they're in good buildings. And the poor people tend to be in shacks that are can be vulnerable. Not all shacks are vulnerable. The worst shacks are fine. They're just cardboard shacks. And if cardboard falls on you, or all palm leaves or something like that, doesn't faze you. That is, again, the worst kind of construction is perhaps the strongest building, or the most safe building in earthquakes. That's kind of a funny controversy. Earthquake hazard. I want to come back to now. Up to now, I have told you that I'm estimating fatalities and injury. Now, that's not very usual. Not many people do that. It's I think on the, besides USGS and GEM and a few other local groups worldwide, I'm the only one besides those two others I mentioned who's doing these calculations. People do standard earthquake hazard estimates, probability of earthquakes and the level of shaking. That's what hazard is. So as per the Indian mythology, I told you before what the Maori and the Japanese mythology says. The Indian mythology says the earth rests on the back of a tortoise whose foot movements result in earthquakes. So next we compare that. As per current assumption, before one large earthquake takes place, magnitude 8, we want this one magnitude 8 earthquake, we're interested. And the current assumption says before it, we have 10 magnitude 7, 100 magnitude 6, and 1,000 magnitude 5, and so on, 10,000 magnitude 4. And all of these have to happen before this magnitude 8 is one magnitude 8 has. So we wait until the bucket is full, and then comes the magnitude 8. And this is the basis on which the probability of the next magnitude 8 is calculated. The fact, however, is contrary to this assumption. The probability of large earthquakes cannot be estimated from the rate of occurrence of small ones. This is the basic assumption that has been made and has never been proven the case anywhere, as far as I know. And I show you now what the facts are. Now, to change the psychology of a entrenched myth, that is very difficult. And it seems I experienced this difficulty. And the introduction was said that I was sometimes courageous, maybe foolish. I add maybe foolish, because I would like to point out to people doing this work that this assumption here is completely incorrect. please consider the facts. This is a photograph of the San Andreas Fault. These are the number of earthquakes as a function of time, cumulative number. That is, anytime I have one earthquake, I add one step, okay? In what? Where is that? Where are these earthquakes? They are in the segment of the Fort Tejon earthquake. That was an earthquake of magnitude caliber 8. And here I'm showing 83 years of earthquakes that are in the catalog, that Richter made, that are complete for magnitude 3.2 and larger. And the duration of this calculation of this catalog is 1932 to 2015. So there are 7. Look at this. See this top number over here, 7. A total of 7 earthquakes in 83 years. Now, this is the map of where these earthquakes were. The rupture segment of the San Andreas is the one in the box, and it's about 3 kilometers long, and the dots are the epicenters of these 7 earthquakes. And according to the hypothesis, one should have expected about 10,000 earthquakes in this figure at the left. That there should be 10,000 in so many years. And as you can see, it's 7. It's not 10,000. Another piece of evidence, look at Northern California. This is a map to locate you. Here is San Francisco. You know, this is the San Francisco Bay here. The solid line is the rupture of the magnitude 8 1906 earthquake, a very famous earthquake. And the dots are all the earthquake epicenters in the catalog of Berkeley. So, where are the dots? If you want to estimate the probability of return time of a large earthquake from the dots, you would say, from the number of earthquakes, you would say they're here. They are not here. The earthquake was from here to here, 300 kilometers, and there are practically no earthquakes along this section. So the probabilities, PSHA means probabilistic seismic hazard assessment. That idea was many large earthquakes, so we have, it means frequent large ruptures. The opposite is true, namely along the 1906 rupture of the San Andreas earthquake, there are almost no earthquakes. There are very, very few. So this is the assumption on the which one calculates seismic hazard. I'm afraid it's completely wrong. There's an additional snag. If you have the catalogs matter, this is maybe only for people who know about earthquakes, for professionals information, but it's also instructional and is full of information for people who are not familiar with catalogs. Look at this. Berkeley has 2 catalogs, and there are reasons for it. I don't want to explain right now, but there's a catalog that covers these years, 1967 to 19. And there's a catalog that covers 1910 to 203. What is shown here? As a function of magnitude, the recurrence time or probability of an earthquake. 1 over recurrence time is probability. So the recurrence time by these catalogs is estimated for a magnitude 8 in one catalog as what is it here, about 5,000 or so. And in the other catalog, it's 100,000. No, what? Yeah, 100,000. No, 4, 5, 10. Yeah, it's 100,000. Unbelievable. This is so wrong. You can't believe it, because we know from paleoseismology that this is the recurrence time. Paleoseismology is excavating faults and dating the previous ruptures, slips, offset of strata, and dating them. And then we have an estimated return time from something like 200 to 300 years. So that the earthquake is actually kind of ready to come, but the catalog would say we have to wait 1,000,000 years. It's completely impossible. Okay, facts concerning distribution of fatalities in earthquakes. This is also something that not everybody knows. and where people won't listen when you tell them. I'm saying between 80 and 100% of all earthquake fatalities occur in rural population. Why is that an important statement? Because at the UN and other places, there is the cry for urban, we have to protect the urban population from earthquakes. Well, it's a very small percentage of the fatalities occur in urban locations. Do I have evidence for that? Sure, of course. I don't say anything without evidence. The sum of small fatalities in settlements exceeds those in cities. That is my point. And why am I saying that? Look at the Wenchuan earthquake. Here is a map of the Wenchuan earthquake. This is a model. It's my model, but it comes close to reality. Each dot is a settlement, and the size of the dot is proportional to the population. So first of all, there are no big city. Wenchuan is the only big city. It's way in the south here somewhere, far away from the earthquake. Nothing happened there. When you look along this line of rupture and high mean damage, it's all small dots, thousands of small dots. And then I have summed up the number of fatalities in settlements smaller than small settlements compared to cities. And this is how I estimated. I did this for 53 earthquakes, and I show you here ordered as a function of earthquake number. I show vertically the percent of rural fatalities. So here is when the number says 1, this is earthquake 1. So in my paper, there's identification what earthquake that is. This earthquake was 100% rural fatalities. There was no city around to be damaged. And then the earthquake number 53 is the most urban earthquake. This was Kobe, Japan. The rupture was relatively short, and it was in an industrially developed area, which means there were no villages at all. So it's only city people who got killed. But look how many of the big earthquakes are above that median line, say 50%. This is the rural population, and here is the urban population, very much smaller. So another way of looking at it is a pie chart. Rural is dark and urban is gray. So in other words, in most great earthquakes, 80 to 100% of those are killed are rural. That's my estimate. This will be true for large earthquakes in the Himalaya in the future, because I think that the small villages will outnumber what happens in the city, in the cities. Okay, how about protecting the rural population from earthquakes? I propose the earthquake closet. Costs are negligible compared to the value of life. It's nothing. This is a photo of a tornado shelter in Oklahoma. And you can see the people were in that shelter. They were unscathed, perfect, okay. And their house collapsed, was totally destroyed. I think one could build the same kind of shelter for in houses that have 1 or 2 stories. And one could use, for instance, if the house has a toilet or a small room, one could strengthen that room. I mean, I could do it with my own hands by buying some lumber and making a structure inside a toilet. And then I would have a safe room in my house if I had a small house somewhere in an earthquake-prone area. Now, why in a tornado, people have time. There is a tornado watch, the tornado is coming, they know they can go into their shelter. But now, how about earthquake situation? Can you get in your closet? Yes, I think you can, because there are P waves, and then the S wave comes later, is slower, but the S wave is the one that delivers most of the damage. The P wave is the small one. So my proposal is that when you feel a P wave in the Himalayas, get into your earthquake closet, and you have 5 to 10 seconds to do this before the S-wave, the big shaking comes. And I have actually experienced that in Kathmandu. I was there for the aftershock of the Burqa earthquake. That was a magnitude 7.2. And it was pretty strong shaking. And I had some time to make a decision of where to go. Another, when rebuilding is necessary, the straw bale house, that is another possibility for dealing with earthquakes in poor area. And there is this is a test house in Nepal, I think, and it's the University of Reno who has developed these types of buildings, and they are not dangerous. They don't kill people. Now, the one thing that is missing is schools and hospitals. I told you that, and I want to just close up with this. Here's a map on the left, Peru. I have every dot on it is a settlement in my data set that would be affected by a magnitude 7 earthquake. And you see that the government list of schools is almost the same as the schools that are in OMS. Open Street Map is OMS. So in Peru, very many schools are known. This is the Himalaya in India. Same size earthquake, magnitude 7 earthquake. And how many schools are available in the Open Street Map? So few schools that we calculate that probably it covers 5 to 10% of the estimated school population. And that is really a shame. One should have a campaign to make a data set of schools in the Himalayas so that one can calculate what happened to them. Earthquakes, no. Models for 7.5 earthquakes in both cases. So I thank you for your attention.